Section: Introduction. In this section, we discuss the motivation behind our work on transformer interpretability. Many current methods, such as probing and sparse autoencoders, focus on extracting interpretable signals from activations. While these methods help us identify relevant features for specific data points, they overlook other aspects of the computation. Another common approach is to evaluate how models generalize to unseen situations, which is useful but not typically classified as an interpretability technique. Both methods have their drawbacks. Probing may miss key features, and testing generalization across all potential tasks is often impractical. We explore a new method for interpreting transformers based on information content. Previous research has shown that well-trained transformers can memorize facts up to about 2 bits per parameter, regardless of their architecture or dataset size. This figure does not indicate the maximum compression rate for all transformers. Since transformers are feed-forward networks, they cannot fully utilize datasets that benefit from recurrence. A good compression algorithm could recognize repeated layers and encode them efficiently, but this does not allow transformers to reduce the number of parameters effectively. We propose that the 2 bits per parameter reflect how transformers can be compressed according to a model that aligns with their architecture. This compression is efficient for factual recall tasks, which do not benefit from recurrence, but less so for tasks that do. We refer to this concept as the native information content of a transformer and will examine how it scales with model size in the context of 2-hop question answering. The native information content is significant because it relates to how well transformers generalize across different tasks. Information compression is linked to learning. The better we model a data distribution, the more efficiently we can encode the data. There is a general consensus among researchers that simpler representations of data generation processes are preferable, and that compression and intelligence are closely connected. We can also predict how generalization varies with different rates of information content capacity. For instance, a theorem-proving system that derives everything from a fixed set of principles will not show increased information content as it proves more theorems, suggesting it can tackle many unseen theorems without further training. Conversely, a system relying on a large set of limited heuristics will require more information content as it learns to prove additional theorems, potentially limiting its ability to address unseen cases. In our work, we specifically measure the information content scaling of transformers trained for 2-hop question answering. For example, if we have a dataset containing questions like, "Who is Bob's boss's best friend?" Mary, a model that memorizes answers independently would require a significant amount of bits based on the number of people and relationships. However, a more efficient approach involves learning a function that captures each person's relationships and applying it twice, which reduces the memorization requirement. This method, however, relies on recurrence, which transformers cannot implement due to their feed-forward nature. Instead, they may need to learn 2 separate functions, with one stored in later layers than the other, to compute the answer. The key takeaway is that 2-hop question answering necessitates feeding answers back into the same factual lookups, which seems to require transformers to replicate factual information across different layers. Section Summary. In this section, we explore a new method for interpreting transformers through the concept of native information content, which reflects how efficiently transformers can compress information relevant to tasks like 2-hop question answering. We hypothesize that this compression is limited by the feed-forward nature of transformers, necessitating the replication of factual information across layers to handle complex queries effectively. Section: Generalization properties of different 2-hop algorithms. In this section, we explore the generalization properties of various 2-hop algorithms. We represent 2-hop questions using a specific format: the first entity, the first relation, the intermediate entity, the attribute in question, and the solution. For instance, in the question, "Who is Bob's mother's boss?" we identify Bob as the first entity, mother as the first relation, Bob's mother as the intermediate entity, boss as the attribute, and Mary as the solution. We note that specifying the first entity, first relation, and attribute is enough to define a 2-hop question. Assuming that our training data only informs the content of certain functions and that any necessary code to utilize these functions is learned perfectly, we can derive different generalization patterns for the three algorithms we discussed. The hash table model will only answer questions that were included in the training data. The two-function composition method requires the first hop to be present in the training data for the first function to learn it, and the second hop must also be present for the second function. In contrast, the recurrent composition method only needs both facts to be present in the training data, allowing them to be applied flexibly. We found empirical evidence supporting the two-function composition algorithm for addressing latent two-hop questions. Specifically, we observed that supervised probes in the middle layers of transformers can extract answers to the first hop of two-hop questions. However, transformers struggle to generalize to unseen questions if the relevant pairs were only seen in one-hop contexts during training. While this evidence is suggestive, it is not conclusive. It indicates that transformers need early access to first-hop answers for effective processing, but we acknowledge that there are many potential algorithms that could achieve this. In our work, we evaluate which proposed algorithm aligns best with the observed information scaling in transformers trained for two-hop questions, providing an independent line of evidence regarding the algorithms used. For our data, we created fictional profiles of people, ranging from 1,000 to 250,000 profiles. Each profile included randomly chosen names and 17 types of relations to other profiles, with no structured relationship between them. We also assigned 4 properties to each person, which could be queried but not used as first hops. We had 21 attributes in total, including both relations and properties. We generated questions based on templates, with one-hop questions asking about a person's relation or attribute, and two-hop questions asking about a relation of a relation or attribute. We simplified our approach by avoiding diverse paraphrases, resulting in a more straightforward dataset. All facts were included as one-hop questions, and we created 7 different sets of two-hop questions to test generalization under various conditions by holding out specific components from the training data. For example, if we held out the relation, mother, we removed all two-hop questions involving that relation while keeping one-hop questions intact. Section Summary. In this section, we explore the generalization properties of various two-hop algorithms, illustrating how different models handle two-hop questions based on their training data. We also present our dataset generation process, which includes fictional profiles and structured relations, to assess the algorithm's performance in answering one-hop and two-hop questions under various held-out conditions. Section: Training. In this section, we describe our training process for transformers based on the llama architecture, ranging from 250,000 to 15 million parameters. We utilized a custom tokenizer trained on our data, featuring a vocabulary of 3,000 words, to keep the parameter count low, as embedding parameters would otherwise consume a significant portion of the total. We implemented the MUP parametrization to ensure effective transfer of hyperparameters across various model widths. Our training employed the schedule-free Atom W optimizer, allowing us to train as long as needed to meet our convergence criteria without predefining a learning rate schedule. We masked all tokens except for the answer tokens and used a batch size of 32 sequences, splitting the training text into chunks of 500 tokens, resulting in batches of 16,000 tokens, including special tokens. We continued training until the loss decreased by less than 10 millionths per step, which typically required about 10 million steps or 160 billion tokens, and this was not heavily influenced by dataset size. For training, we used one hop question for every 10 two-hop questions, unless we were focusing solely on one-hop questions. Next, we defined dataset entropy as the entropy of a random variable representing our entire dataset as a single sample. This random variable includes the uniform selection of names and birth dates from their respective possibilities. We assumed the receiver knows which tokens can be used for each answer type, but not the specific names in the dataset. We ignored terms related to selecting viable tokens since they do not scale with the total number of profiles. We focused on how the entropy of selecting names scales with the number of names, contributing n times the logarithm of the number of possibilities to the dataset entropy. For one-hop question answering, the entropy of an individual answer for an attribute is the logarithm of the number of possible answers for that attribute, leading to a total dataset entropy based on available attributes and relations. For two-hop question answering, we explored different models. In the recurrent model, the dataset entropy matches that of one-hop questions, while in the two-function model, we treat first and second-hop relations as independent, requiring them to be sent twice. In the independent model, every answer to a two-hop question is treated as independent, leading to an entropy equivalent to that of a one-hop dataset with the number of relations multiplied by the number of entities. To measure the information content of our trained model, we calculated the difference between dataset entropy and the sum of cross-entropy losses for all answers and tokens. For one-hop models, we used the probability of a correct answer across all tokens, and we applied a similar approach for independent two-hop questions. For recurrent and two-function compositions, we computed an effective loss for the one-hop functions that contribute to the two-hop answer. We found that our one-hop training runs achieved an information capacity of about 1.6 bits per parameter, which is less than the previously reported 2 bits per parameter. Although we replicated earlier results with different hyperparameters, we observed that transformers displayed a stacked curve behavior in information content scaling with dataset sizes. These curves started below the 2 bits per parameter capacity, indicating that the models had not learned much beyond random guessing. The content curve approached the 2 bits per parameter line before leveling off near the dataset entropy. Our results aligned better with the two-function composition model than with the alternatives, although this is not definitive evidence since we tested a limited range of dataset and parameter sizes. The curved relationship between information content and parameter count may arise from several factors. If the models perform poorly on either hop, learning the composition algorithm becomes challenging. Additionally, models might allocate some of their information budget to memorization, which could increase as they near perfect performance on the training set. This could explain the growing generalization gap with larger parameter counts, although this trend might reverse at very high counts. Lastly, our method for estimating two-hop capacity may be overly simplistic, potentially affecting the curve's shape. We also trained deeper models and observed a similar but less consistent trend, likely due to not adjusting optimizer hyperparameters for the deeper architecture. Section Summary. In this section, we trained transformers based on the llama architecture with parameter counts ranging from 250K to 15M, utilizing a custom tokenizer and the MUP parametrization to optimize performance. We measured information content through dataset entropy and found that our one-hop QA models achieved an information capacity of approximately 1.6 bits per parameter, supporting the two-function composition model over alternatives, while noting that the scaling behavior of information content is complex and influenced by factors such as memorization and model performance. Section: Two-hop generalization. In this section, we explore the generalization abilities of transformers without chain of thought in two-hop problems. We find that their performance aligns with our earlier predictions. Specifically, without chain of thought, the models do not generalize when any part of the first or second hops is missing from the training data. However, they do generalize when entire questions are excluded. This observation builds on previous research by systematically excluding different components of two-hop questions, unlike prior studies that removed facts from any two-hop context. We note that during training, every fact was presented within one-hop questions, indicating that facts learned in this context do not contribute to the two-hop components unless they are positioned correctly in the question. The situation becomes more complex with chain of thought. We never observed generalization for withheld first entities, but we did see it for withheld second entity attribute pairs. Other withheld elements showed inconsistent generalization across different training runs. We believe this inconsistency may stem from competing heuristics, where the model balances low probabilities of certain tokens appearing in specific positions against applying the correct rules for two-hop questions. Although we did not train many models in this setup, it seems that generalization may depend on the specific training seed. This suggests that scaling, which aligns with recurrent composition, does not perfectly predict generalization. We also speculate that models learn both independent memorization and generalizing algorithms for two-hop reasoning. In our experiments, we trained models to memorize two-hop answers independently, sacrificing one-hop learning. These models failed to generalize and showed lower information content compared to those that could generalize. We used a dataset with fewer relations and maintained a ratio of 1 one-hop question for every 10 two-hop questions. We found that reducing the loss for a two-hop question had a greater impact on overall loss than reducing it for a one-hop question. Our observations indicate that these models struggle to learn one-hop question answering beyond random guessing. Their capacity scaling aligns with independent memorization, and they do not generalize to withheld questions. We hypothesize that the models initially focus on memorizing two-hop answers due to their greater impact on average loss. However, due to limited capacity, they become stuck in a local minimum, where improving one-hop performance requires sacrificing performance on memorized two-hop answers. Consequently, they remain trapped in a non-generalizing state, despite having the potential to perform better if they could learn to generalize.